Hi, I'm Lewis Davidson. I'm going to talk about concurrency today. Most importantly, concurrency in SQL Server and when you're doing relational database kind of operations. So let's get started. My super brief contact info is DRSQL. It's my Hotmail address. It's my email address, my website address, DRSQL at drsql.org. And then my GitHub, where I'm starting to put sessions like this, DRSQL GitHub. So, all right, so we're going to talk about a certain set of things about concurrency. We'll start out talking about just ever so slightly about hardware. And hardware makes a big difference in, what you can do concurrent and what you can't do concurrently. We'll talk about transactions. I'm hoping this was labeled as intermediate advanced. If you don't know what a transaction is, you'll hopefully be able to catch what that is. It's not that difficult. Isolation, how does two people are doing something on the computer at the same time, how might those two connections interact? How might they not interact? Time is more important than any other of the concepts we'll talk about, because time and concurrency is all about time. If we didn't have to do things at the same time, if everybody could just schedule their jobs to run and nobody had to wait and see if anybody else was working in the same data at the same time, then we wouldn't have any problems. But yes, time is where all of our problems come in for concurrency. We'll talk a little bit about how SQL Server enforces concurrency and what are the mechanisms and how do we control those mechanisms as much as we can. SQL Server runs on a tremendous lot of hardware now, but you can't expect this machine to run what a really server class machine can run. It's just not going to happen, because the server class machine has lots more hardware, has lots more paths to move data around, it has more faster CPUs. When you start to run, many people at the same time, you try to run thousands of connections, you could probably do it on both machines. But what you're going to get out of them is completely different. How many things can occur at the same time? So we're not going to talk too much about those details, because, let's say nobody's using any of the same resources other than the hard disks and the CPUs. Well, the hard disks and CPUs are still going to be bottlenecks, and they're still going to be concurrency points. And that is not something you have a whole lot of control over at SQL Server today, or even in your code. That's just, we send a lot of stuff to the server, it queues it up and does it. Yes, I'm not going to stop every time I say something stupid like that on my recording, because I'd still be recording it even as we're doing it live. So just keep in mind that the level of hardware you use is definitely going to play a point in how much you can do and how fast things are going to run and how many things will seem like they can run at a time. Just understand that hardware is foundational. It's important to have the hardware run as good as humanly possible. But it's a lot about budget. So let's talk about stuff we can control. Transactions. What is a transaction? It's a container for a set of operations in your relational database. So let's say you're going to insert a row into a table. Well, there's always two things that have to occur. One, it's got to go into memory. Second, it's got to be in the transaction log. I mean, you can turn that off with delayed durability. So there's only one kind of one thing that's got to happen logically. But each one of those, that transaction log write and that memory write has to occur before you can move along. So transaction bundles those together and says, I got to finish all the pieces, and then I got to make them durable. And once I made them durable, they're saved to disk, and I don't have to worry about them anymore. I mean, saved to memory, saved to disk in the transaction log. I don't have to think about them anymore. And that's great. Sometimes you may, try to update every single row in your entire database, and that may be billions of rows. And you may find out on the billionth row that you got something wrong, and you have to roll back. That becomes a real pain. So accelerated database recovery in 2019 actually improves that by changing the way transactions are rolled back and managed. I'm not going to talk anymore about that. It's just something to look up if you're building a lot of databases. And a transaction gives us atomicity. So if we have 50 operations, we're trying to insert 50 rows, or we're trying to do 50 different statements into 50 different tables. Atomicity gives us, we can say in this transaction, everything must finish before it completes. Okay. Now the purpose then becomes a container. And the transaction is in a container for that atomic operation to finish and that atomic operation to be durable. During the time that container is running, we have to then say what else can happen. Someone else may go in and try to delete all the rows from the table. Like when we were doing that billion row operation we just talked about a second ago. Someone tries to delete all billion rows. What happens? They have to wait, right? Sometimes, depends on the model, but typically they have to wait. And when they get finished, what happens? Someone has just sat down and they have modified a billion rows. They've changed some values in a billion rows, and the next person has deleted them. Well, that kind of containership, we have then, each container gets put into the transaction log, and that is then able to be reapplied or unapplied depending on the scenario we're talking about. So a transaction is a container, and it gives us this ability to do one operation or all operations and treat them as one thing. And then we want to make sure they're separated from other transactions. That'll be the point we're coming up to next. A few more little bits about transactions. You can nest transactions. If I say start a transaction, then with begin transactions, the statement, begin transaction, begin transaction, begin transaction. There's 4 transactions started, but technically inside SQL Server, there's only 1 transaction. So you can undo a transaction by using a rollback command. We'll see all these in the upcoming demos. Beyond the regular sort of transaction, we have what are thought of as autonomous transactions. And some RDBMSs have this as a separate kind of thing you can start. But in SQL Server, we have identity columns and sequence objects. So when you do an insert into a table and it has an identity column, it goes out, it starts a little transaction, says, give me the next identity value, grabs it, sets the pointer to the next, sets the identity to the next row, next value in order, and then it undoes the transaction, but the external transaction is still running. If you roll back that transaction, roll back that insert, that identity value is lost unless you go back and do some things that are to the table, which are not part of the DML, the standard DML. For a sequence object, they are, but you can reset a sequence object. But it also works under an autonomous transaction in that if you say, give me the next value for sequence X, it gives you the value, and that's not part of the main transaction. But there is a transaction that has to coordinate so 2 people don't get the same sequence value. All right, so I'm going to assume, again, this is an intermediate advanced. We're going to just assume that you understand the basics of begin transaction, commit transaction, rollback transaction. If not, they will be shown in other demos, and it's fairly straightforward what they're doing. Okay, so we have our connection, this package of operations that have to occur. And then we have to ask ourselves, how can one connection affect another transaction, another connection? So the classic example is the lost update. Someone over in here goes out, selects the balance of the table, and they said find out the balance is 500. The next person gets the transaction, and they find out the balance is 500. So now this connection says, let's update that data from 500, add 500. So we believe it's now 1,000. Over on this connection, they subtract 30. They both commit the transaction. One of them wins. So the final transaction final balance in this scenario is 470. Well, that's clearly not the desired operation. So we have to then make sure this doesn't happen. Well, we know that something in SQL Server, we'll talk more about that in a second, but something in our relational database is saying, hey, I'm modifying this row. Don't let another person modify it till I'm finished. But I've already got the balance here, and I've written my code as such that I'm going to update the balance to the value that we gathered minus 30. So even no matter what SQL Server is doing, Because of this time effect, as I've already alluded to, you're going to lose data. Now, if you'd written the code as set balance equals balance plus 500 without worrying about this select, then we wouldn't have lost data when we did this operation. Because balance plus 500, whenever this is finished, commit tran balance minus 500. And we know that banks, generally will just let us take out money and then just fine us to death for it. But if you have situations where you want to make sure that you have a positive value or a negative value, you don't want to lose data when you're doing your operation, and you certainly don't want it to be in a dangerous situation. So if you're medicine, if you're giving medicine, and we want to say select how much medicine has patient X been given in this hour, and then the next person runs the exact same query, we don't want to start applying medicine to that person. We want to make sure this person cannot have anything changed that they've looked at or done something to. And then we want to make sure that whenever we get here, any blocking we've done, if we've said nobody else can do something, that this next connection can't just then take things that they believe about the data and move along into it. Okay, so let's step next to a lot of places to look here. All right, so now we get to the different kinds of phenomena. When we're in one connection, another connection does something to the data we've grabbed. So phantom rows are new rows. I run a query, I write select star from table. There's one row in the table. I write that query, then I run it again. I get back 2 rows. That new row is a phantom row. And that can be a problem for certain sort of operations, like if I'm doing a balance, a balance and I have to sum all the data. When I come back, I don't want any new data to have been added because my balance will have changed. A non-repeatable read is a read where data has vanished. So I write my query. I say select star from table. I get back 1 row. That second row is okay. It's not a non-repeatable read. The second row, the first row is the exact same that when I queried it. Then that is a repeatable read. That's a read that's fine. But if somebody updates that data or they remove that data, then we have a non-repeatable read. And that can be a problem for things like foreign keys. If I want to say, here's a new row, is there a foreign key value that exists? Yes. Well, I come back in the next operation I do, somebody deletes that row and it's gone by the time I commit my transaction. My data is not consistent. That's one of the ACID properties is consistency. When I do my commit of a transaction, everything should be consistent with all the checks that I've checked. A dirty read is seeing data that may not have actually existed. So if you are doing a query of a table and someone's in the middle of an operation, go back to the lost update, and they update all the rows in the table and they say set value times 10 for every row. And at the last row in that process, it hits a constraint that says that value is too high or that value is too low. And so you have to stop the transaction. Well, someone else who is writing a query sees the dirty data, the data in its dirty condition, then that's a dirty read. And they may be making decisions on values that never actually exist in the table. It's really, really kind of terrible for your data consistency. And as a data architect, I'm most concerned about things like coding of concurrency and check constraints and things, because I want the data in my database to be consistent. I don't want to have any rows where the primary key is duplicated. I don't want to have any rows where the excuse me, where the oh my goodness, where the foreign key value is gone when I start writing the query, or the parent row is gone. Anything that I need to exist, I want it to exist, and I want the database server to make sure it's done correctly. Previously committed data. Now this is alluding to version-based concurrency stuff, and this is where we want to say, hey, when you go start a transaction, start an operation in the database, you're going to see the data in the way that it looks until you get finished. And this is great because most of the time when you're running a report, I don't want data to be able to change from the time when I start my transaction. I want it to be the same until I get done. Because someone may, as I may read the parent table, someone may change the child table, and I end up seeing different rows. I may want to go run the query again. But even if the data has changed completely, when I started my query, that's what it looks like at the time. There's definitely some problems and concerns with that, the way you handle it, but it's a great way to increase concurrency of your data access. So you don't go in and pick and choose and say, I will allow dirty data, dirty reads, and phantom rows, but not non-repeatable rows. You choose a transaction isolation level. And these are the standard settings which let you say, I will allow these anomalies. The isolation level, read uncommitted, this says we'll allow dirty reads, phantom rows, and non-repeatable reads. This is just basically show me what's on the physical disk when I'm passing through. Give it to me. Doesn't matter if it's going to exist. Doesn't matter if it's actually right. I'm going with it. That's one we typically do not want to use. The most common isolation level to be used in the code I've worked with is read committed. And this allows phantom rows and non-repeatable reads. What it doesn't allow is you to do dirty reads. So I can't go out to the disk and do a fetch and get back a row that's not yet committed. And this is really good because most of the data you want to access is just, I want to access the data that's been committed. Someone said, yes, this is good. It's not in the process of being inserted. So that's perfectly acceptable. It has a few downsides though, like I said, for foreign keys, summary data, things like that. Snapshot isolation level gives us previously committed data. So it may be older data, but it'll be consistent no matter how many times you run your query. It will always come out to it. You will always get a consistent view. A repeatable read allows phantom rows. And this is good for foreign keys. This is good for any time where you need to say, does a person have children in the table? Does this row have a parent row? Any kind of things where you just want to check the existence of one or more kinds of things. And then serializable doesn't allow any of these phenomena, but it doesn't prevent people from looking at data. It just prevents people from changing data. If I go out and I query the table, an entire table in serializable isolation level, no one will be able to insert or update rows. And I'll show you this in some example code later, demo code. But it doesn't prevent you from reading. It does prevent you from writing to it, which is very useful. We have two kinds of problems that you have to deal with. One is synchronous access. Two people are trying to update the same row. One of them is blocked. One of them has to wait until they finish. When the other one finishes, it opens it up and lets them go. The other kind of operation is asynchronous access. Asynchronous access is somebody grabs a version of the row here. Another person grabs a version of the row here. Changes are made here by a third party. Now, if this person over here is making changes to the row based on the data they have over here, are they going to overwrite changes? What about this person? What about this person? And the problem with this isn't so much that it's caching is a problem. We know that we think about these things when we're doing caching. So if I cache a million rows or 1,000 rows or even one row, and I'm doing something to it, it's kind of natural to say, hey, does that row changed since I used it? Is there a chance something may be different about this row? But it's less likely to think about this when you have a synchronous collision. Like I said, one person updates the row, another person's trying to update the row. They're both updating the same column. They're both updating the same value. They're updating to something different. When this connection one, which is over here, finishes, then they're done. They release their hold of the row. This connection goes ahead and makes their change. You don't feel it. In SQL Server, you don't feel that You don't feel that happen. You don't feel that happen if it's blocked for a micro, if it's the difference is a microsecond or a minute. Whatever you started out with your value, you're thinking, you're believing you have, you need to do some sort of check to say, hey, has the data changed since I grabbed it first? And we'll look at a few ideas on how you do that as we move along. All right, so how do we enforce this? The first is locks, but we hold a lock. We put some sort of hold that says, I'm doing this with the data. You can't do anything with it. The other is versions, and that's where as I said, everybody sees the data at a certain point in time. I hold these versions. Connection 1, connection 2, and connection 3 all see different things. And they have to, at the finish of their connection, say, has anything changed? Am I still in the situation I'm in? We'll show that in the demo as well. Okay, so let's talk about locks. And you may notice I've changed uniforms here. It's not because I'm trying to show off my keen sense of fashion, clearly. I had some audio problems, so I'm kicking back in. Locks are resources or tags that tell you someone's using a resource. Somebody's, querying a table, there'll be a lock on the table so it can't be dropped. Every row you have access, you're currently accessing, there's going to be a lock on there to say, don't, nobody else change it while I'm reading it. And when someone else is changing it, there's going to be a lock that says, don't touch it while I'm changing it, because you don't want to look at dirty data. Some of the things we can lock are databases, tables, pages, rows, keys, ranges of data, schemas, extents. There's some other things you can lock when you're doing other operations, but these are the ones typical we'll talk about. And then there's different types of locks. There's a shared lock that says, hey, I'm looking at this data, but I'm not planning to make a change. I'm not making a change to it. There's an exclusive lock, which is typically used when you're making modifications. You can put these locks on, using a hint, but they behave a little differently when you're using hints than when you're using just regular isolation levels and things. There's an update lock, which says, I'm planning on making changes to these rows, so I'm scanning for the rows I'm looking for. But other people can still be looking at it. It'll be changed to an exclusive lock if I actually do make changes to the data. And stability locks, which are something you'll see if you start using in-memory objects a little more, because they don't use other kinds of locks. But these locks tell you someone's using a resource, don't make changes to the things that has the stability lock on it. Okay. And then a subtype of intent. So if I'm locking a row in the table, I'm in a query, I accessed a row and I have a lock on it. There'll also be a lock placed at different levels higher up in the chain. So the row will have a shared lock, perhaps, or an exclusive lock. And then the page will have an intent lock on it that says someone below me has a certain kind of lock. And then at the object level, there'll be an intent lock. And this makes sure that anybody who wants to take an incompatible lock lower in the chain doesn't try to take that lock at the high level, because someone already has things incompatible lower. And that is there to cut down on deadlocks. So we don't accidentally put on incompatible locks. Then we have compatibility of locks. I've mentioned that word already. And that's saying certain kinds of locks aren't compatible with other kinds of locks. Like shared and exclusive obviously don't sound like they're compatible with one another. Two shared locks are compatible with themselves, but an exclusive lock isn't compatible with shared, nor would an exclusive lock be compatible with itself. And what happens is sometimes one connection has resources that the other needs, and they end up with a deadlock. And I've got a slide with a little more detail on that in a second. Lock compatibility, I've already mentioned this a little bit. You can look at this slide and see there's certain types of things aren't compatible with one another. The thing about it is why query optimization matters to concurrency. You think, okay, everybody's running slow, they're using more resources. Well, that's one problem. But if you are touching lots of rows, then you're locking lots of rows. So if I say update row where first name equals, well, let's say where identifier equals X, and there's only one row in the table that says identifier equals X. If I don't have an index on that row, I will scan every single row in the table, and then I will have locked every single row in the table. In the read committed isolation level, I may not keep those locks, but I will have had to take those locks. In the higher levels, I will have to keep the locks. So we have this problem that if you touch every row, then you lock every row. So it's really kind of important not to make sure you're only locking the things you need to do. So, and it doesn't fit very well, and it's very hard to kind of see in the lock metadata because of the way read committed works. Like I said, we don't hold the locks, so you won't see them at the end. If you run the query and then you go look at the locks, which I'll do in the demos, you won't see the locks you're worried about. A deadlock. So a deadlock is very simply one transaction X has resources that transaction Y needs, and it needs transactions that transaction Y already has. And then the vice versa is the true. So there's no way that either one of those connections could finish. So one of them has to be killed. Deadlock, killed. Yes, it's a very, very gruesome sounding process. Even though it is a gruesome sounding process, it's one of your least bad things that happen in the database. All right, so let's kick on with a demo. Okay, so I'm going to start out by creating a database. I've created a few tables. Let me scoot down to there. I have one table set up for doing things where I can use a single table, and it's just a table. I have a value for it to access, and then I have this padding to make sure that rows are bigger than will all not fit on a single page, because some optimizations can be done with data that's all on one page that can't be done otherwise. And I'm just going to insert some random data, more or less random data. You may recognize a few of these names if you're of a certain age. And then when we get down to the demos that need two tables, I've got a table with a person and a table with an interaction. And the interaction is related to the person table. And that'll let me show you things with foreign keys when I get to that. And just a little bit of just random data. In the downloads, there's a file called lock viewer. And this lock viewer will give you the ability to look at the locks in the database. And we're going to start with this called locks, this file called locks. So we're going to demo what kind of locks are held when certain operations are occurred. So I'm going to use my matters of concurrency database, and I'm in SPID 75. I'll set that up so that's the only thing we see. And we start out right now, all we have is a database lock on the database because all we've got is a connection. And that connection, this database locks keeps the database from being dropped. If you need to know who's in your database, if you're trying to drop a database, that's how you do it. So we're going to start out by running a read uncommitted transaction. And, I'm not going to have a lot of time. So, just in your head, think really quickly, what's going to be locked when you do read uncommitted? And the answer is, in that transaction, nothing. There's no locks are being held or taken for reads. Anytime you do a modification to an object, no matter the isolation level, it will, in fact, take the same locks no matter what. All right, so if we do read committed, we know read committed allows for non-repeatable reads and phantom rows. So if we run our query, I'm in my transaction, what's going to be locked? Well, it turns out the exact same thing as the read uncommitted data. And why is that? Well, that's because it held locks as you went along, taking a lock, looking at grabbing the data from that row that's being locked, then releases the row, releases the lock, grabs the next row, locks it, grabs the data, unlocks it. For a repeatable read transaction, when you query that table and you go look at the locks, you're going to find that every single row has been locked. It's a small table, so it didn't have to escalate to a table lock. If it's a really humongous table and you start running out of memory, it can escalate to the to a complete table lock. And we can look here and we can see that each page has a intent shared lock at the page level and also at the object level. So this means that none of the rows that I've modified, that I've read in during this process, can be modified by anybody else because I have this shared lock. And shared locks are not compatible with exclusive locks. So let's move on. Repeatable read, now serializable. If you do serializable, we're doing select star from table. This means everything has been locked and I can no longer insert data into this table in another connection because I have a lock to the not just the objects in the table, but the range of data in the table. You're always going to see this FFF thing when you do a select star. It's like the entire table. And each one of the pages that's locked has, or keys that's locked, excuse me, has a range lock on it that says this range is being taken. And again, we go back to the pages. You can't really do much with a resource description, but it helps you to correlate those if you have a bunch of things locked. So we've locked the entire table. So let's turn on a snapshot isolation level. And let's do a snapshot lock query. And if we take a look at the locks here, there's no locks being held because we looked at the versions. Actually, versions are being held, not locks right now. So now we take this bit of information and let's go a little deeper. Now let's update a single row in read uncommitted. Let's see what's locked. So we come back over to our lock viewer and yes, there's going to be locks, but now we have an intent exclusive lock at the table level, an intent exclusive lock at the page level, and then an exclusive lock on the row that's being modified. And again, we can look at the page and see all the rows that are on the page. Obviously, in most tables, you ideally will not have 4,000 bytes of A's repeated in your table. If we're in read committed isolation level, and we go back to that and we do the update, you're going to see the exact same things are locked. This is because, again, we don't hold locks on things that we've read, but we do hold locks on things that we've changed. More things were locked along the way, but you know, it's kind of hard to tell without doing something like repeatable read. So if we do that and we update this row, we come back over here, we can see that it's touched every one of the rows and it has an intent exclusive and intent update on all of the other rows. So we have that update lock. We have that intent update lock that was placed. It was changed into an intent exclusive lock for the rows that were actually modified. All right, so now let's move along to a little bit of a competition. So here's where building demos and running demos is just as hard as building tests to do this sort of thing. Because what you have to do now is I have to have two connections at least. And I have to make sure that they run at the same time and that we get what's happening. So take, for example, in serializable, I run a query. If I just run this in serializable without the transaction, it'll run an in. This isn't, which is a normal thing you would do, right? But if I want to test the competition between two connections, I'm going to need to set up a transaction, hold that transaction, and well, get in the right database as well. And then make sure that the next user also has this going on. So if I have this connection over here in serializable mode and I try to run another query in serializable mode, it'll absolutely work. And that's, you know, we've talked about the compatible locks. You'll see that this is connection 77 and this is connection 66. We come back in here and you're going to see that we have the same set of locks on both tables. So two users now have these serializable connections. So if you have to have a lot of users doing these serializable level connections and transactions, you're going to have a big issue eventually of concurrency because no one can update or modify any data in that table. And particularly if you don't do a very good job tuning your code, then you're going to have a problem. So let me roll these back. Now, one thing that's interesting is if I'm in a serializable transaction, I say with xlock, and I run this query. And I come look at the log viewer. I see on my 77 connection, I have page locks that are exclusive. I have exclusive locks on everything, range exclusive locks. No one's getting access to this data theoretically. But I come back over here in my scenario 2 query and I run my query. I'm not blocked. And this is because read committed doesn't get stuck at just an exclusive lock. It gets dirty data. Just beware of that. Don't think that you can put an exclusive lock and then every reader is going to be blocked. Anybody in the higher levels would be blocked, but not a recommitted. Particularly not if you change it to recommitted snapshot, which we'll look at here in a few minutes. Okay, so scenario 3 is I'm going to set up a reader. I'm in a writer. It's going to update the value of the column Fred to uppercase. And then in this connection, I'm going to say, show me the value of Fred. And we'll see that Fred is a uppercase. But if I go over here and I roll this back and I look at it again, still in the same transaction, I'm going to see the Fred as the lower case, which is not desired at all. But let's try read committed. So I come over here, I update this value again, and now I'm going to query for the value of Barney. Well, I'm blocked. And I'm blocked if you look at the lock viewer because we are waiting on a key lock for that column because I've got to look at that row and say, hey, does this row Fred? I can't tell that because I don't know what he's updated it to. This connection over here has updated it to whatever it wants to update it to. So this is where tuning comes in. And it's very important. So let me roll this back. And now if you can put an index on it that's not unique, or if in this case, it's better as a unique constraint. If I go in and I update the row, over in this connection, I want to look at the row that says Barney. I am not going to be blocked from looking at it because this the connection on the left side does not have a lock attained for that data. So I'm not going to be stopped at that juncture, which is a very, really important part about why we need to tune. Tuning is the most important part of concurrency, along with knowing what can happen. Because there's the things we're going to talk about now, we really wouldn't want them to happen. All right, so in recommitted, I do my update. And it pretty much doesn't matter, like I said, when you do an update, what isolation level you're in. So I've updated this value. All the values were row doesn't equal Fred. Whether I can run this query or not depends on the locks that were taken. If we look at the locks, in this case, it took a key lock on every single row, but it did not take a page or table lock that blocked me. If it's a much larger table, this may end up being blocked when only one row is one of the rows we're not looking at. So in recommitted, I come back in the other table. Somebody else adds some more rows to the table. You notice we're not blocked from adding the new rows. But if I come in here and I ask this query again, I'm still not locked. Still not blocked because those new rows that are still dirty, we know because this is a unique index and I've got this value and it's not modified. The pages in the index that might be modified if something with an A started it, if the alternate Fred and alternate Barney might have been in something that it would have read, it would have known because it would have been blocked. It would have tried to modify the index in that place. So now we know that we're not blocked. Everything's still good. Totally good. No big deal. We're going to leave that open. And one more last blatant. I know this is supposed to be advanced, but don't use read uncommitted, because occasionally stuff like this will happen and you'll be stuck looking at data and the customer will go, why does my data look funny? And you'll go, I guess it was because something happened with a customer. Well, no, now it looks right. Well, I don't know what your problem is. I think you were seeing things. I never like telling customers they're wrong, particularly when it's my own fault or some programmer's fault. All right, so we're gonna do this one about read committed holds no locks. We don't need to show that. You can keep running these queries, and somebody can insert, update, or delete. They'll only be locked as long as you are reading it, right? So when you read it the next time and you come back, it will not. It'll be added. Foreign keys are a fairly interesting thing in this scenario because, as I mentioned, if you're writing your own foreign keys, you need to go and make sure that whatever row you said would exist still exists at the end of your transaction. But at this point, what we've got is, will that happen for us? So let's insert a row. It references person ID equals 1 and scenario 8. So now let's go in here and can I update that row, but not update the foreign key? Well, I hold a lock to the foreign key, and the answer is no. There's no lock to that foreign key. There's no lock held that would prevent me from doing that. And this is because foreign keys protect themselves. When I run something that needs the rows in the other table, it goes and checks, and it comes back and it returns, and you'll see that connection 77 doesn't have any locks to the person table, just the interaction table. 66 has locks in the person table. But if I come over here and I insert a row and this row is locked, now I do get it because it's going to check. It doesn't, locks are held on the whole object, not just the column. So when it has to go over there, it doesn't know what's going to happen with the row. So now we're in this standoff. I can't make any changes. But it's not the foreign key that's holding the lock. So when you think about foreign keys taking more time to do your operations, it is definitely true. But they do not lock anything in the opposite table, generally speaking. Now, again, generally speaking is always one of those terms where you're like, yes. So when do they? Well, the case is if, and I'm gonna skip this. This just shows if you're in serializable mode, no matter what, you're still not gonna hold any locks in the table. It's the exact same locks we showed before. Okay, so if I do a query such as this, and I'm going to run a query, delete from person, where name is Arnold, we're not going to get any data. This would fail if there were any interactions that existed. So we know we don't. And here we are in person. The person table has locks, but there's no locks over in the interaction table. So now we come over to this scenario here. And if I try to update the table, I get blocked because I've dirtied the row and it is waiting on, wait, it is here. It's waiting on the person key that I have locked till it's finished. Okay. And it's rows, not the table lock. So let's roll that back. So we know there's no child rows in the table. But let's change this to a cascading delete. And this gets a little bit more interesting. Oh, you're thinking, yes, let's hope it gets more interesting. But I must be in a transaction. I am. Okay. So I've changed this to a cascading delete. So when I do my delete now from Arnold, we know there's no data in the other table, but the locks are actually one more thing that causes an issue. We have the intent of locking some rows in the table, so we get this intent exclusive lock. Okay, so the intent of exclusive lock on the interaction along with the person rows that we modified. You know, the locks that are being held are not compatible, but they're not on anything the other thing has a problem with. So it doesn't have, it never tries to take an exclusive lock. It has two intent exclusive locks, but they're compatible with one another. Okay. However, if we do something that requires a table lock, and I'm going to force it here, now we're blocked because an intent exclusive lock may be compatible with another intent exclusive lock, but the shared intent exclusive lock is not compatible with the intent exclusive lock, because an intent exclusive lock says, so I may be locking something exclusively down below. So multiple things may be locked exclusively by multiple connections. But this is saying I want to read the table. I want a shared intent exclusive lock on the table, and that's not compatible. Yeah, that's a little bit of an interesting thing with cascading deletes. Finally, I'm gonna skip over that other thing. Read committed snapshot is of all the things we have in SQL Server, this is the go faster button that actually really helps. We had a project back in 2005 where we were making Microsoft CRM do way more than Microsoft CRM should do, and the only way we made this happen is with using read committed snapshot. So let me set this to recommitted snapshot on. This is the greatest command here, the rollback immediate, just kill everybody who has a connection. So what the excuse me, it's a statement level snapshot. So just like read committed doesn't take any locks, read committed snapshot doesn't hold on to the versions that you've held in the background. So if we say update all the rows in the table, and we come over to this other connection and I read all the rows from the table in a transaction, I don't see that I've uppercased them. I see the way the table looked. This is the data that was in the table. I put in some more data. I come back and I run my query. I tried to run the entire table. I still don't see it. I actually started in the transaction. I don't see those two new rows. I see the old alternate rows. And we can do this all day. Only when this is committed do I actually come back and see the changes. I'm still in the same transaction. Lastly, very briefly, a deadlock. I start a transaction. And I update the row with Fred. I come over here, I update the row with Arnold. Over here, I update the row with Fred. I'm blocked. Over here, I update the row with Arnold. And now we're in a untenable situation. This row is continued. This one was deadlocked. So we have to say, okay, you finish your transaction, then go back and finish yours. So the thing I want to make sure it's clear is concurrency is a lot about tuning and what do you need to make sure exists? What are the things you need to make sure happen? So it's really complicated. Testing it. I mean, the hardest part is you can't really always test like I'm doing with the application with users. Certainly can't do it with just people sitting down and typing in data into a table. You have to get down and actually run these tests so you know what's going to happen. All right, let's get back to the slides. We're all working on live data and we're blocking each other. We're just going to start out every transaction as much as possible with a view of the data that's ours. So we look at the data. It's like you have the entire database to yourself. So you don't have to worry about what you're doing and blocking each other. It's just when you go to save the data, you have to make sure, are you consistent? So everything's implemented lockless. We're going to be looked at a commit time, or sometimes when things occur. We're never going to have a place where in a true multi-value concurrency control, where you're having to sit and wait for something to occur with another connection. You may have hardware you have to wait on. You can't get all the data immediately, and disks and whatever. Even memory is not, completely without latency. But any kind of conflict with other users will be done at commit time. It's typically considered optimistic concurrency control because of that commit time thing. So if I'm going to go out and 2 months later, I'm going to finish something in 2 months, 2 minutes, 2 seconds, anytime later, I've done a lot of work. I don't want it to crash. So, or optimistic that there's not going to be a collision in our operation. So it works best with less modification collisions, short transactions, and it's definitely going to make integrity checks a lot more difficult. And we'll see that in the demo, because where before a foreign key didn't block, a foreign key will block. Well, not block, but will have issues with things like repeatable reads and having to do something again, because I can't tell you, I can't go and see, does that row exist? Even system doesn't allow itself to go look and see if somebody's made a change until you commit time. And at commit time, you can go look outside of your container. It's typically considered a pessimistic model to do locks, because we think we're going to be connecting to the same rows and we want to coordinate that, and then we want it to finish. But again, some of the things we're going to do with pessimistic locking are very similar to what you have to do with optimistic locking, because you have to say, hey, has anything changed? And that's what happens in the pessimistic locking due to the time consideration. So every modification is a new physical resource. Every time you do an update, we're gonna modify a row in the table and say that row that you had been modifying was good from when it was originally created or modified last to now. And then we're gonna have to insert a new row for that future row. So you have the available to see what it looked like at previous times and see what it looks like now. So if no transactions are using that previous version, we can throw it away. But if they are, we need both those versions. And if a bunch of people are making lots of changes and a bunch of people are having transactions out there that are still using those versions, you can end up with lots and lots of versions of the rows. That's why you'll be instructed when you start using memory optimized tables to have a lot more memory than you have data, because sometimes you're going to need to have multiple versions of the data available. Cleanup process, go back and clean up those rows once people are no longer using your transactions. There's two versions of this currently implemented in SQL Server. One is memory optimized tables. They started in 2014. They've been improved in most versions of SQL Server since. And they're largely completely based on versions. It supports snapshot isolation level, repeatable read, and serializable isolation levels. We'll talk about how that's done, even though it looks like it's a snapshot isolation level problem. And we've already looked at read committed snapshot already. Um, this makes versions in a TempDB, or if we talked about it, accelerated database recovery earlier, or in a special store inside your database. There'll be versions of every change you make that you can go and then query and see the previous versions of the data, which is very, extremely good for performance. It's just, you have to be careful. You know that you're looking at old data. Don't make decisions that might affect someone with that. Something may have occurred outside of your view. So we have this memory optimized table. And what you'll see is you have 3 rows. One says USA, 2 USA, and 1 and 3 is Canada. And inside the table, you'll have a couple of indexes. Here's a hash index on identity value. And the hash is, it basically takes one, hashes it to something. We're going to say it hashes to 3, and then 4, and then 6. And, the hash buckets, if you chose 3 hash buckets or 2 hash buckets, and it's in powers of 2, but let's say you have 2 hash buckets, 2 of these rows, 2 of these identity values would have shown to the same bucket. Well, if someone makes a change to the row, what happens is you get this additional row. So identity column value 3 is here, 4, 6. Well, now there's 2 rows that go to 6, hash to 6 because it's the exact same value. So you start going down these chains. So we say, here's a 6 value, found it in the index, and it goes to everything that's hashed to 6 is now in this chain. And the pointers are all built into the row of the data in the memory optimized structure. They are just as fast as a clustered index because the indexes are built into the structures. Well, for country now, the value changed. So at timestamp 50, you come down here and you query, give me all the rows that say USA. So you find USA, 1, it hashed to 1, and it says, okay, yes, it's USA. Does the timestamp match? Yes. So that row would be returned. Does the timestamp match here for 50? Yes. So this row would be returned. If you come back in here at 150 and you ask the same question, you get two different answers. So at the end of your transaction, let's say you're in a repeatable read isolation level. At the end of your transaction, it can tell if any new pointers have been added to the chain. It can see the rows that you had access to had they changed. It was a timestamp changed. For serializable, it has to literally go out to the query table and do a query that you would write to say, hey, anything that has changed, can it change? And you'll be able to see in the physical structures of the index that there are these special phantom lookups. And I'm going to show you just a few of these. I don't have a tremendous amount of time, but we'll see what we can get through. All right, to get started on memory optimized stuff, I'm going to use the exact same demos, but I've built another database here or not another database, but another set of tables which use the exact same data and exact same structures before, except instead of demo, I'm putting them in demo mem. So the big thing to get here is that when you're in a multi-value concurrency control, I run this update, and until I commit, I'm not really affecting anyone else. I'm only affecting anybody else if they happen to interact with a row I'm modifying with in a non-compatible way, which I'll show in a few minutes. But if I query this row for Fred, I don't see it uppercased. Okay. If I start another transaction, I still don't see it. I won't see anything. If I commit, I won't see anything. Now, if I commit this operation, so if I'm over here and I query the table and it gets committed, I don't see the change. Oops, sorry. Am I apologizing too? I don't see the change until I commit. So until I get done here and I commit, now I'm going to see it as large, but I won't see that until it's committed on the other side. Now this is where I say I'm doing demos for memory optimize to match the other kinds of things. You're going to have to update the data to look like it did originally, or you'll end up with a mess. Okay, so the reader in read committed. So if I'm in here and I do a query, read committed snapshot, I do an update. So now I come over here and I'm in repeatable read. I run my query. I see Fred. Okay. If I commit this, totally fine because nothing has changed physically yet. If I restart my transaction, I look at the data, I see the lowercase here. Now, if I commit this, now the rows changed. So I expected no changes to my rows. So if I query the data, I still see it as what it originally was. But when I commit, I get the crash. So this is repeatable read validation. This is where you have to really be really careful with what you're thinking about. Because the first few times I did this demo, like, for myself, 3 or 4 years ago when I wrote it, I was like, hey, everything works. I don't have to worry about it. That's great. And then you're like, oh yeah, because I kept rolling them back. And that just didn't work out very well. So I do my query in serializable mode. And I come over here and I do my update to the table that changes the rows. When I commit this, I get a repeatable read validation error. So I was in serializable, but I get a repeatable read validation error. Repeatable read validation is two steps. One is, has any of my structures that I've actually touched changed? And then it runs a query for serializable checks. So let's do this really quick. Let's start another serializable. Let's insert a row. 2 rows, sorry. And now let's commit. Now we get a serializable validation because we didn't change anything, but we did get the validation. So you can see in your indexes that certain indexes have been used for phantom rows checks. So we want to see what phantom rows are out there in the index. When we looked at the structure, you saw the rows. Well, whatever time period I am in, I have to go run the query that says, are there, the repeatable read is, are there any pointers to things that are newer because my transaction time had changed? But then serializable runs that query and sees if the timestamps are the same as the timestamps at my time period. So it really is looking at both time periods. Okay. So that's kind of an interesting part of how this all works. Delete those extra rows. All right, so where things get kind of fun is I update Fred, and this connection updates Fred. Well, I don't get blocked. I get an error. It says, you've attempted to update a record that has been updated since this transaction started. So blocking is this. This is blocking. This is what blocking looks like. Blocking is, I don't think so, try again. Which is really good, right? And this is faster. If your transactions are short and you don't have like humongous batches of things to modify, this is really easy. But here is the biggest optimistic problem. I'm going to insert a query. I'm going to insert a row with alternate Fred in this connection. I'm going to insert a row with alternate Fred and alternate Barney in this connection. And I'm going to remember to run the query. Note that they're in both sides, but look at the results of that autonomous transaction we talked about earlier. So alternate Barney and Fred got different keys, but everything's still running. So if you want to go in and modify, insert a million rows, and you're doing it on 2 connections and you're doing the exact same inserts, as long as you're not using the same physical resources yet, you're okay. But when they become physical, so we commit that row, that works. But I commit this row, it says, sorry, serializable validation feature failure. So then you're told to go run it again. And this time you get a more expected error of violation of unique key constraint. And the transaction is still open. So, simple enough. I'll skip that one. It's available if you want to do it. It's very similar to this. And then, okay, foreign keys are different, very different than in on disk. Here I do a query. It's going to check the person table. Well, if I update that person table and I don't change the key value and I check it, its text is upsized. Over here in my view, I see text as lowercase. So when I try to commit this, I get a repeatable read validation. So foreign keys do suffer from concurrency issues in memory optimized tables. Okay. So let's talk a few minutes about asynchronous considerations. What happens is typically two users fetch data, 2, 3, 100, whatever, and both wish to make some sort of update to what they currently believe is true. No one wants to lose any information in this process, so time separation may be hours for cache data, or it could be microseconds, as we've already talked about for malloc. So what are ways that this is handled? One is chaos, and we just let the last writer win. And this is a possible solution that's not as bad as it sounds for some types of problems. Sometimes it's okay that we lose the data. But remember, our goal was no one loses any information. So let's skip past that one. That's probably not the answer that we're looking for if that's our goal. And we're really, using our brains for this process. Optimistic locking, we want to check the cache data to see if you still had it. So when you do your update, you take all the data you used to have and all the data you have now, changes you made, and you pass it by the table and you say, has any of the data changed from what I believed it to have? Sometimes you may use a row version, a timestamp, a row last modified time, some value you've changed, some version you've updated. You can also use a hash of the data. So you can do a hash and put all that into a binary value. That works very, very well as long as it's sufficiently good hash. I mean, the chances of two hash values being different, representing this different data depends on how complex your hash is. Even checksum has always done fairly well. I mean, I've never had seen any actual problems, but theoretically, it's definitely a problem. And I know people have had problems out there in the world. I've just never seen it. Or pessimistic locking. You just say, dang it, I'm going to take this everything that I touch, and I'm going to exclusively lock it. I'm going to modify it. I'm going to use an application lock. It's a really good way to do a single-threaded operation when you need them. Okay. A hybrid of these are really a possibility because sometimes you're trying to deal with hundreds or thousands of rows, and you're not going to save off hundreds and thousands of rows if you're trying to update some value as a DBA and make sure your data is correct. So you're not going to do that, right? You're going to go ahead and just update it and probably lock everybody out of the database. Some things you're just going to go, I don't care. I'm going to update this value, and if someone else is updating it right at the same time and they lose data, that's okay. I mean, that's not a problem. But ideally, as long as you're really thinking about these things, it's probably not as big of concern as you might think. As we've showed, I mean, things like foreign keys and stuff is really kind of handled by the system. So let's wrap up. The problems are complex, and it's a matter of thinking, testing, throwing as much realistic operations as you can, trying to make people do the same kind of things, act like 50 members of the same household are all trying to update their family data at once, see what happens. Is there any way that they can hurt themselves? And realistically, probability and dumb luck is about half of the world's, salvation. We can all see that with the current reason we're all doing this virtually right now, that bad things are happening, but a lot of good stuff happens just by dumb luck. I mean, you don't happen to bump into something, you don't happen to get it right. So, and it looks better, and then it's bad. But the real thing here is, it all depends on how much it costs if your integrity fails. If you have concurrency issues that cause a concurrence and integrity fail, what's the cost? What happens if you get that wrong? We want to look at throughput. We want to make sure queries are processing as fast as they reasonably can. But we also then want to look at the cost of an integrity failure. What happens if it fails? What's the likelihood of there being a problem? But what happens if it fails? That is the most important thing. If you cannot answer that question of what happens if your integrity fails, then you should not be writing this code, right? This presentation code, the current version of it will be on GitHub. My version of this, the versions from today, will be on my website in a Dropbox. Twitter, I'm DRSQL. My blog is at Simple Talk. And where I talk about some concurrency, I talk about a lot of database design kinds of topics because that's my thing. And I'll leave this up here for about another couple of seconds. You can always rewind eventually. And I just want to say thank you. This is some of my pictures I take at Disney. I'm a big Disney fanatic. Disney Pick a Day, Twitter. This is one of my favorite kinds of things, are firework pictures to celebrate the moment. And I noticed it's gotten darker in my office as I keep talking. Time changed yesterday. I'm recording this on November the 1st. Thank you to Microsoft. Thank you for supporting Data Platform Geeks and SQL Server Geeks. Thank you for Data Platform Summit for having me. Go ahead and post your selfie with your hashtag. Post your selfie enjoying the sessions. Give your feedback. Follow them on Twitter. And thank you. It's been grand.